The following program is presented by the National Speleological Society.
What I'd like to do is to walk you through a series of slides that talks about the geology, in particular the volcanic geology of planets and satellites we see in the solar system. Well, in the exploration, the geological exploration of the solar system, we have come to learn that the surfaces of planets, solid surface planets now, have been modified by four basic processes. Those that are generated from the impact cratering and gradation. These are things that are happening on the surface of the planet from the outside, and then processes that are happening in the interior of the planet, and these are tectonic and volcanic processes. I hesitated here a little bit because I just noticed these slides were just made endogenic and exogenic are reversed. It should be the other way around. I'm sorry I had to try this out on you, but I'm giving a talk at the Jet Propulsion Laboratory next week, and so I'm going to have to redo this. Well, the point is, we're very interested in volcanic processes as a means of shaping planetary surfaces. The next slide points out that volcanism, either active volcanism or volcanism in the geologic past, has happened to varying degrees on all of the terrestrial or the inner planets. And these planets are listed in order of knowledge. Obviously, the planet we know most about is our own home planet, Earth. The planet we know least about is Mercury. The point is, we do see volcanism, evidence of volcanism, on all of these objects. Next slide. We turn our attention to the outer planet satellites now, and the one that is listed there on top is called Io. That's one of the moons of Jupiter that, in fact, Galileo discovered in the 1600s. The thing that we found when the Voyager mission flew past there is, in fact, that active volcanism is occurring on that satellite. But it's a style of volcanism that we haven't seen before, and I'll talk about that later. The other outer planet satellites, some of the important ones here we see, one form of volcanism on or another are all listed there. The point is, those bodies are composed mostly of ice. And so when we talk about volcanism, we're talking about a slushy ice mixture that's erupting on the planet. It's a different kind of magma. Remember what a magma is. It's simply molten material. In this case, it's water. Next slide. Well, what's the role of lava tubes in planetary exploration? The thing that I list here is something that you all are very familiar with. Lava tubes play a very important role in the emplacement of lava flows. And when we look at the surfaces of planets and satellites, we're very interested in working out the geology of the surfaces. And when we see evidence of lava tubes and lava channels, this tells us something about the properties, the rheological properties of the lava flows that we see. There are also implications for the style of eruption, because we know that lava tubes and channels form only in a very distinctive style of volcanic eruption. And of course, when we map out lava tubes and channels, this helps us identify the source areas for the lava flows that we're looking at. And in that context, it's an aid to geological mapping, which is a fundamental thing that we do when we study other planets and satellites. And then finally, when we put the whole picture together, it helps us understand what the surface history has been. And that's the ultimate goal in planetary exploration, is to derive the geological histories for the planets and satellites. Next slide. Well, in particular, we have the opportunity here on the Big Island to observe active volcanoes, and we can learn about the geological aspects of lava tubes and channels. We know that, in fact, the lava tubes are very effective in retaining heat. This allows the flows to flow longer. And when we look at some planetary cases in a minute, you'll see how important that is. We also know that there is some erosion that can take place where there's actual down cutting by the lava tube channel system. And until the past decade or so, the significance of that really was not appreciated. We see the development of levees where there's spillover from the lava channel, or through the development of distributary lava tubes that extend out laterally from the main tube. Again, very complex geology. The point that Bill was making, lava tubes are much more complicated than many of the volcanologists had appreciated for many years, at least volcanologists in the 50s and 60s. And of course we see from mapping, this is a very effective mechanism for getting lava, magma, from the point of eruption out long distances. On Earth, those distances can be many, many miles, as you well know. On other planets, they can be hundreds of miles. Okay, very important mechanism. Next slide. Well, many people have had the chance with primarily eruptions that began with Honolulu here on the Big Island to observe the formation of lava tubes, the roofing over channels and so on. And in recent years, this is, we've added a lot to our understanding of how tubes form. The next slide shows a series of eruptions at Honolulu here, Big Island. And we can see the rafted slabs that are carried along on the open lava channels, filling in a pit crater, and then the development of a roof further downstream. Well, I show this simply to point out how important the eruptions here on the Big Island have been in gaining an understanding of how lava tubes work. Next slide. I'm going to turn to the other planets. The planet that we know probably the most about after the Earth is the Moon. When you look at the Moon, you see those large dark areas. Those are lava flows. They are essentially the same kind of lava flow that we're standing on here on the Big Island. It's basaltic lava. How do we know that? We brought samples back from the Apollo missions and from the Soviet missions. We have a good understanding of what the geology of those lava flows is like. The next slide shows part of the lunar surface, and you see the sinuous channel there. And I think Bill was one of the first people to suggest that features like this on the Moon were in fact lava tubes, lava channels, flat sections that we see very similar to what we have on Earth. There are differences though. Biggest difference is the size, because that channel that I show there is nearly 1 kilometer wide. That's wide, okay? And so the dynamics of the lava flows there must be a little different. But we can trace those back, these features that are called sinuous rills, to their points of origin, and it helps us identify the source vents for the lava flows that filled in the low-lying areas on the Moon. And from the samples, we know that this happened very early in the history of the solar system. The surface that you're looking at there, that dark, smooth surface, is about 3 billion years old. That reaches right back into the very early history of the solar system. And it tells us that the Moon was active in the early history of the solar system. And from other observations we've made, we know that the Moon has been relatively inert since that time. The next slide shows something that happened this past December. For the first time in some 2 decades, we obtained new information on the Moon from a spacecraft with the Galileo mission. And this is the spacecraft that in fact is on its way to Jupiter. And in the process, the launch trajectory requires it to loop around the inner solar system to gain energy before it gets slung-shot out to Jupiter. In the process, we have flown past the Moon and have seen the far side of the Moon with modern instruments for the first time. And the next slide shows the information from that spacecraft of the far side now. The dark area on the right is the near side. Those are the lava flows. And what we see on the far side, we see those little dark areas. Well, in fact, those are small local eruptions. Now, we knew those were there before, but we had not viewed them with modern instruments that tell us something about the composition. And this flyby happened last December, and so now we're in the process of analyzing those new data to try to understand what the composition of the lavas on the far side is like. This is new information. The next slide, we now turn to a planet that is held in fascination by many people. It's the red planet, nicknamed the red planet Mars. Red because it's covered with rusty dust, but we also see dark areas there. And in effect, we see a surface that has been modified by a lot of geological processes, and in particular, volcanism. Well, this is a chart that was prepared from images acquired about 15 years ago. And what are you looking at there? Volcanoes. Enormous volcanoes. This is the Tharsis region on Mars. And the next slide shows the largest of those Tharsis volcanoes. Here it is. And what's superimposed on it? The Hawaiian Islands. Okay, to the same scale. And here is the Big Island, which in fact is composed of several volcanoes merged, and yet all of those are much, much smaller than a single large volcano that we see on Mars. There are similarities though. The general shape is the same. We see a complex caldera that was the primary source vent for the lavas. And when we look in high resolution, we see a series of lava flows fed by lava tubes, spreading the lava out to the flanks of the volcano. The dissimilarities are, it's huge. And there are no obvious rift zones like we see here on the Big Island that control the location of the volcanoes. And from what we can tell, the volcanism on Mars to build that shield volcano spanned a much longer period of time. The next slide is simply a diagram to give you an idea of the scale. There's Olympus Mons, the Mars volcano, 15 miles high. The caldera itself is 45 miles across. To the same scale, here's Mauna Kea, and there's Mount Everest. So, difference in scale. Why is that? Different plumbing? We don't know. What's happening in the interior of Mars to enable this large volcano to grow? These are things that planetary geologists are working on. Next slide. Well, here are a couple of photographs that show Olympus Mons again. Here's an enlargement on this side, and you see that channel up there, parts of which are roofed over. Beautiful little lava tube system. And you can see the individual lava flows that spilled out of that channel to build up the flanks of the volcano. This is simply one of literally thousands of similar systems we see on that Martian volcano. The next slide.
What's the scale on that, Ron, on that tube?
That tube, the section that's shown there is about 30 kilometers long. That section, and it's only a tiny section of it. You can see the scale. The box there on the left is where that image was taken. Next slide. As impressive as the shield volcanoes might be, we also see many sheet lava flows that fill in and build up the plains. And in fact, something like 80% of the volcanic surface on Mars is composed of this kind of lava flow, not those that build the shields. And in this case, too, many of these flows were in place through lava tubes and open channels. Next slide. Well, next summer, we will be launching a new mission to Mars. It's called Mars Observer. And this is a spacecraft that will carry a camera system. In fact, the camera system that's being built in my department at Arizona that will enable us to photograph any place on the surface of the planet, objects as small as this chair. And so one of the things we're going to do is to fly over those lava flows where we've already identified lava channels and tubes and try to get some high-resolution images of them and see if we can pick up some details on them. This is a mission that's going to launch next summer, as I say. And again, will be new information on Mars. Next slide. Let's turn our attention now to the outer solar system. And again, this simply shows the relative sizes of the major planets in the outer solar system with our dinky little Earth in the middle. Well, and it's not Jupiter, Uranus, Saturn, and so on that we're interested in, but it is the satellites of those major planets that we want to see. And the next slide shows, again, the view of Io in the background, where active volcanism, the first active volcanoes off of Earth, were discovered here on Io some 13 years ago. The next slide shows one of 9 active volcanoes. This has been computer enhanced, so the colors are greatly exaggerated to bring out the tail. And you see that blue bubble on the horizon is an eruptive plume rising above the surface some 100 miles. Now that's quite an explosive eruption. And when we look at the spectral signatures, that is to try to get some understanding of the composition, we see a strong sulfur component. And sulfur is a volatile element, and something is causing it to erupt explosively on the surface of Io. The next slide shows the surface of the planet now. It is colored reddish-orange, and again, the spectral signature is that of sulfur. And what we see is sulfur being heated in the interior of the planet through tidal stresses. I'm not going to go into detail, but it simply is the push-pull mechanism as Io orbits Jupiter. It's constantly being flexed. And because the crust is being flexed, a lot of frictional heat is generated, enough to melt the interior of Io. And that sulfur component is then erupting explosively onto the surface. Everything you see there is the result of volcanism, of at least the sulfur variety and maybe the rocky silicate variety as well. Now, when this information first became available, we got very interested in sulfur as a volcanic material. The next slide shows some of the places where sulfur volcanism, where the eruption of sulfur is known to occur. Lava flows now I'm talking about, composed of sulfur. And you see the big red dot out in the Pacific Ocean there is where we're residing right now. Up on Mauna Loa, there is a small sulfur flow that occurred, it's thought to have occurred in the 1950s or so. The next slide shows that area that we visited. It is on the southwest rift zone. This is looking up the rift zone up to the summit of Mauna Loa. And this rift zone has been a site of a lot of volcanic activity. You can see all of the channels that are there and the cinder and spatter cones. Well, the next slide shows one area on the southwest rift. This is one of those small spatter cones. And all that yellow stuff there is sulfur. And for scale, I point out, can you see the person standing there? Yes. All right. It's not a big flow, certainly not as big as the one that occurred in the 30s in Japan, but nonetheless, it's very instructive to look at it. And the next slide shows this part of the flow in detail. Very pure sulfur that erupted out onto the surface and then flowed about 75 meters down the hill. Well, the thing that I found interesting is that within it is a very small lava tube that was feeding the lava flow out to the front. And again, it was in effect an extension of the vent to allow the sulfur to flow further than it would have otherwise. The next slide shows a diagram, and here's what we think was going on. The crosshatch pattern is the cinder and spatter cone where the flow occurs. And I show the rubbly zone on the slope of the spatter cone. And what happens is, as you know, fumarolic gaseous activity brings elements up to the surface, and when it comes close to the surface in contact with the atmosphere, it's precipitated. Sulfur is a volatile element. Sulfurous gases coming up through fumaroles led to the development of sulfur deposits within the cinder and clinker. And this was the source for the sulfur flow. But that's only part of the story. What was required was for that sulfur to be melted. And so what happened in the 50s is there was an eruption. The bottom diagram shows the intrusion of basaltic magma, which has a temperature of some 2,000 degrees Fahrenheit. And as that material came up to the surface, what did it do? It melted the sulfur. Sulfur has a very low melting temperature. And so it was the proximity of the basaltic magma intruding into the cinder cone, raised the heat of the sulfur, and then let it flow out from where it had been trapped. And that's how the deposit was in place. Now, this same mechanism probably is what has happened at the other sulfur flows around the world as well. So it's a combination of basaltic volcanism and the presence of sulfur that led to the flows. And interestingly enough, we see evidence of both sulfur volcanism and silicate volcanism on Io. It's through studying this feature that we think we understand better what's happening on that moon of Jupiter. Next slide. Well, the other outer planet satellites have less silicate, less rocky material, and are more ice-rich. And this is the current model that shows the interior, one of the other moons of Jupiter, Ganymede. And what we think happens on these icy objects is that the ice water down in the mantle of these satellites is heated and is erupted onto the surface as a type of icy volcanism. That's kind of a contradiction in terms, isn't it? But that's what's going on. The next slide shows other icy objects, very smooth areas associated with long fractures, and we think those are places where this icy slush erupted onto the surface. The next slide shows the Galileo spacecraft again, that is currently on its way to Jupiter, and it'll get there in 1995 and will take images when it's put into orbit around Jupiter of Io, of Europa, and the other moons of Jupiter. And one of the things we plan to do is to follow the eruptive sequence of those explosions on Io and try to get an understanding of the dynamics that are involved. Because the pictures that I showed you before were taken during what's called a flyby mission. The Voyager mission simply flew past Jupiter and its satellites, and over a period of a few hours took some little snapshots. And we didn't really have a chance to see how the eruptive plumes evolved. With Galileo, we'll be in orbit for 20 months around Jupiter. And we'll be taking images of Io and the other satellites on a regular basis. And so we can build up systematic coverage of the surface. And at much higher resolution than Voyager took. Next slide. What object is this? Anybody recognize it? That's Neptune. Neptune is interesting because The other planetary object that we see active volcanism is one of the moons of Neptune, and it's called Triton. The next slide shows Triton, and you see those dark streaks up on the upper part of the picture? Those are eruptive plumes also, where geyser-like activity shoots dark material up above the surface of the moon, and then it's carried downwind for some 75 kilometers and leaves that deposit. And the point is, Earth is not the only planet that experiences active volcanism. We've now seen it on Io, and now we've seen it on this moon, Triton. There may well be other active volcanoes in the solar system. We simply haven't had a chance to catch them yet, but at least two other objects have active volcanoes. Well, in the geological past, as I said earlier, almost all of the planets and satellites have experienced volcanism in the past. Next slide. What I've not talked about very much yet is the planet that's often called the sister planet of Earth, and that is Venus. Venus is about the same size and density as the Earth. And because of those characteristics and its position in the solar system, it's often thought to have a similar history, and yet it is drastically different from the Earth. The atmosphere is the main difference. It has an atmosphere that is 90 times denser than the Earth. In fact, standing on the surface of Venus would be like being on the seafloor at a depth of some 400 feet. The pressure is that great. And the temperature on the surface of Venus is extremely high. In fact, the surface temperature exceeds the melting point of lead. The surface is completely covered with thick clouds. Clouds that are composed of droplets of sulfuric acid. Not a very pleasant place to be, but a very fascinating planet because of the volcanism that's there. Because of the cloud cover, for many years we were not able to see the surface of Venus. Optical camera systems simply could not see through the clouds. But the Soviets, a number of years ago, flew a very primitive radar camera system in orbit, gave us our first glimpses of what the surface looked like. More importantly, beginning last year, the Magellan spacecraft by the United States was put into orbit and is returning a fantastic array of images. The next slide gives some of the characteristics of Venus volcanism. Where do we get our information? The Soviets have landed on the surface of Venus with automated spacecraft in some 12 localities and measured the composition of the rocks, characteristics of the atmosphere. An earlier U.S. mission told us what the general topography, the shape of the surface was like. We also have geophysical data. Magellan is the main information source, though. The spacecraft that is currently in orbit and returning digital data. In fact, the amount of digital data that's been returned thus far, less than 1 year, exceeds all previous information from all previous missions to the solar system. It's an enormous amount of information so far as raw bits of information. I'm not going to go into detail on this. The point is, the bottom line there, you see foliatic basalt, subalcalic basalt, and so on. What is that? Again, the same rock type that we're dealing with here on Hawaii, the same rock type that lava tubes form in. And so, from this information, we might suspect that lava tubes exist on Venus as well. The next slide shows an artist's rendition of what the Magellan mission is like. It is in an inclined polar orbit, and it has completed the first mapping cycle that's given us about 80% of the surface of Venus now. Now it's coming back and filling in the gaps and is providing stereoscopic information on areas that we've seen before as well. The next slide shows Beautiful volcano. Where? On Venus. What kind of volcano? Well, this is exaggerated. The vertical scale is exaggerated. In fact, it is a shield volcano. Again, very large though. But look at the lava flow that's coming down toward you. Now the color is artificial here. We don't really know what the true color is like. This is a picture taken by a radar camera system. Okay? And it's not an optical image. You have to keep in mind the difference. It's a radar picture. Next slide shows one of the volcanic centers, a caldera there, and you see these collapsed pits extending off to the side. This picture covers about 200 kilometers across, and those kinds of surface features should look familiar to you. Yes, next slide. And here are some individual lava flows. The scale is at the bottom of this. Okay? Again, very similar to what we see in basaltic eruptions here on Earth. Same style of volcanism, only now we can see it for the first time on Venus as well. The next slide is a summary. This is the last slide, then I'm going to show you a video. The point is, planetary volcanism. We know that volcanism is one way that planets get rid of heat generated in the interior. For the terrestrial planets, the amount of volcanism is proportional to the size of the planet. Big planets like Earth and Venus are dominated by volcanism. Little planets like our moon also experience volcanism, but not to the same degree. For the inner planets, basaltic volcanism is the main style. And because of that, we should expect to see lava tubes and channels formed in those flows. And in fact, we are seeing that. And then finally, when we look at the shape of volcanoes and relate the morphology of the tubes, this tells us something about the styles of volcanism that were involved in the evolution of those surfaces.
The preceding program was produced by Paul Stevens for the National Speleological Society Audiovisual Library. The music was composed by John Manchester. My name is Lee Stevens, and we hope you enjoyed the program.